Okay, everybody, 2 o'clock, welcome in. Not a lot of announcements today. We're going to continue our fourth couple notes today. We're going to talk about cross products. I think maybe some of you have maybe seen cross products in previous math classes, but maybe not. We're going to go through the whole rigmarole with cross products today, so you'll learn about those in their full depth and detail. Yes. Announcements, I did post a new homework right before lecture. This is going to be on, forces and moments, couples, whatever, stuff that we're kind of talking about this week. It will be due next Wednesday at the beginning of class. All right. I took a silly dad joke as my meme today. Dream where I weighed less than a thousandth of a gram. I was like, 0 mg, OMG. Kind of funny. I think it's funny. All right. Well, let's pick up where we left off. Okay. So last we left off, we were talking about this new kind of twisting force, which we called a moment. And I went through a bit of a detailed example with a lug wrench and how the forces that you apply to a lug wrench would sort of create a twisting force or a moment at the lug nut for this particular example. All right, so we talked about what this sort of force is and what a free body diagram might look like if we were trying to include this sort of twisting force in part of our free body diagram. And the idea here is that, yes, we're applying some forces on this wrench with our hands, but there's something going on here at the lug nut. We're applying this sort of twisting force. And this twisting force we're going to call in what is known as a moment. Okay, and it's sort of like this torquing action. And the idea is that we're applying force far away on our rigid body, which is our lug wrench, but that is inducing some moment here, right? And the idea is that, all right, there has to be some relationship between sort of these forces that we apply on our lug wrench and the power of this particular moment that occurs here, the directionality and the strength of that sort of twisting force or that moment. And yes, there is a relationship. And if you thought about intuitively how you might increase that torque or increase that moment, you could bring your hands out farther on the wrench. So there's some relationship between the distance that you are on the width of the wrench there, or you could just increase the force at which you apply on the wrench, and that would give you an additional torque or an additional moment on that nut as well. So there has to be some relationship between distance away from the lug nut and the amount of force that you're going to apply. And there is a relationship. And to talk about and discuss that relationship further, we need to introduce a new mathematical topic. And that mathematical topic is the cross product. And so we're going to represent moments with a double arrow or a curved arrow on our free body diagram. And to calculate them appropriately, we need to go through a little bit of math right now. And that math is cross products, or what are sometimes called vector products. So there's this relationship between these applied forces and the resulting torque or moment. And we have a new vector math technique, and that is the cross product. So that's what we're going to talk about today, and that's what we're going to introduce today. And then after we introduce all the mechanics associated with what is a cross product and how do you calculate it, given a couple of vectors in space, we'll talk about the math in executing a cross product to calculate this moment, which is this sort of twisting force. Okay, so let's get into that now, and we'll talk about cross products. Okay, so cross products are sometimes called vector products. Or you might see it as cross product. And this is a technique that involves two vectors that are in space. All right, so the new concept, this idea of a moment is coming. But we need a bit of math beforehand to sort of get ourselves there. Vector products or cross products. Okay. So, we've worked through this class a little bit so far and have done some vector math, and now we've actually done some in 3D with your 3D equilibrium problems. So we should be a little bit comfortable with three-dimensional math at this point. Now I want to introduce this new idea of a vector product, and I'm going to do it pictorially first, and then we'll put some words to the page. So first thing I want to do is I want to put two vectors that are on the same plane. So let's draw a plane that exists in space. It might just be represented as like some rectangular figure here that exists. This is some plane in space. Okay, and let's say now that we have two vectors that exist in that plane. It's a two-dimensional plane, and we have two vectors, and they're both emanating from a particular point here. So there's a point in space, two vectors emanating here from that particular point, and we're going to call them vectors P and Q. So here's P, and here is Q. And we'll say that there's an angle between these two guys in space, which is an angle of theta. So here, this angle here is the angle theta, for clarity. All right, if we have two vectors that are in a plane, and any two vectors can be in a plane, right? The cross product, or the vector product between the two of them, has a couple of rules that we follow. And let's just write those in English now, and I'll show you what that is. Okay, so the vector product of two vectors P and Q is defined as the vector V, subject to some kind of constraints, so which satisfies the following. This is a colon here. First, the line of action of V is along an axis which is perpendicular to the plane containing P and Q. So we'll put that in words. So the line of action of the vector V, that is basically the direction in which it acts, is perpendicular to the plane containing P and Q. All right, so what does that mean? After we execute the cross product between P and Q, there will be a resulting vector that occurs, and that vector will be perpendicular to the plane containing P and Q. That's sort of step number one. All right, this will all come together pictorially in just a second, but let me get all this information down first. Secondly, the magnitude of the vector V is the product of the magnitudes of P and Q and the sine of the angle between them. Okay, so if you want math language, that is the magnitude of the vector V is the magnitude of the vector P multiplied by the magnitude of the vector Q multiplied by the sine of the angle between them, which we call theta. Lastly, and I'll discuss this in just a second, the direction of V is governed by the right-hand rule. And I'll show what that is in just a second. All right, so let's show on this picture the actual vector product of P and Q. All right, so subject to these kind of rules here. All right, so the line of action of this vector V is perpendicular to the plane containing P and Q. All right, so that means that if we're perpendicular to the plane containing P and Q, I've either got to come off the plane this way or come off the plane this way. That's kind of my only option for the resulting vector product. All right. Second, the magnitude of this guy is the product of the magnitudes of P and Q and the sine of the angle between. All right. So that'll become important in just a second when we discuss these magnitudes in a little bit more detail. But basically, the magnitude of V has to follow this particular idea. So that means if P and Q are perfectly aligned with each other, right on top of each other, the magnitude of V is 0. Okay? So the sine of the angle between them is the sine of 0, which is 0. Okay, so that's important. We'll talk about that a little bit later. And finally, the direction of this guy is governed by the right-hand rule. I'll explain that in just a second. So let's actually put this now on our figure. If we're going to execute the cross product between P and Q and get a resulting vector V, our resulting vector V, if we're doing P crossed with Q, is this vector here. This is V. And we would say that this is the cross product between P and Q by expressing it in this way. V is equal to P cross Q. This is not a multiplication sign. This is a cross, an X. I guess this is why they don't really use X for multiplication after, like, you know, 9th grade, because you don't want to confuse multiplication with cross when you come to vector math. Right? Now, how did I know that the direction of V was up instead of down in this particular image? Well, that comes from knowledge of the right-hand rule. And now we got to sort of explain what this right-hand rule means. All right. So the order of the cross product is important. So here we have P crossed with Q. And the right-hand rule is a little bit difficult to explain or wrap your head around at first, but after you've sort of done it a few times, it will be perfectly clear. So the way that this works is the order is important. P comes before Q. And we're going to use our right hand to help us figure out the final direction of the vector V. And the way that we do this is, everyone kind of get your right hand out here because this is going to be important. P cross Q, we're going to stick our right hand in the direction of P. So imagine that you're standing on this particular point right here, and you stick your arm out in the direction of P, right? Then you want to curl your fingers in the direction of the vector Q. So everyone kind of think about sweeping your fingers through that angle theta, kind of pointing towards the vector Q. The direction that your thumb points will be the direction that the vector V is going to result. All right, that's the general idea. So you might visualize this with a picture that we have in the notes. You can try to draw this if you if you're a good artist. I'm not going to even attempt this. But oh boy, got chopped off. But here is a picture from the notes of your right-hand rule. So in this particular example, this person's got the right hand. They've sort of initially launched their fingers here in the direction of the first vector P. Okay, then they're sort of curling their fingers in the direction of theta towards Q with their right hand. And their thumb, wherever it's pointing, points in the direction that V will ultimately point. The reason that we do this is because generally we use what are known as right-handed coordinate systems. So if you thought about a traditional like XYZ axis, it also follows this same rule. So a traditional XYZ coordinate system looks something like this. If you thought about the right-hand rule for this particular coordinate system, you would first stick your hand in the direction of X, you'd curl your fingers around towards Y, and your thumb would stick in the direction of Z. This is a right-handed coordinate system, or what is known as like a proper coordinate system for rectangular components. It would be kind of funny if you saw a coordinate system that, you know, didn't look like this, but looked like this. Okay. This is not a right-handed coordinate system. If I thought about sticking my sort of arm in the direction of y and then curling my thumb, sticking my fingers in the direction of x, curling my thumb towards y, my thumb would point down, which is the opposite direction of where z is actually pointed in this particular image. So this is not a proper coordinate system. This is a left-handed coordinate system. But every single coordinate system that you use in the real world, or that you should use, is a right-handed coordinate system, and it follows this general idea, is that you would first stick your fingers in the direction of x, curl towards y, and your thumb should be pointing in the direction of z. That would be a right-handed coordinate system. And our product, a vector product, follows this same idea. Now, I've been very specific here in this drawing above that the vector v is p cross q. If I went the other way, I could create for myself, let's say, a v prime, which is the opposite direction. And if we wanted the same vector but pointed in the opposite direction, we could do q cross p. And this is an important distinction to show that the directionality of the vectors is important, all right? So if I stuck my right hand in the direction of q, if you want to think about like doing this yourself, and then I curled my fingers in the direction of p, my thumb would be pointing downwards. And so we see the resulting direction of v in this particular situation is downward. And this is an important distinction for the cross product, right? So a little bit strange to understand, and maybe you don't really have a concept of how this is related to moments quite yet, but I promise you that we will get there, all right? So, that's the basics, and that's the general idea. Now let's maybe have a thinking moment here and talk about this. All right, we know that the magnitude is the following. The magnitude of the vector v is the magnitude of the vector p multiplied by the magnitude of the vector q times the sine of the angle between them. So I kind of have a challenge question here for you guys, and that is, what orientation of P and Q results in the magnitude of V equal to 0? Okay, I've already kind of mentioned one of them. Anyone in the class take a stab? So 90 degrees would be the greatest value of V that you could achieve, because the sine of 90 is 1. So think the other way. Yeah, right. So the orientation of P and Q, which results in the vector V being equal to 0, is if theta is equal to 0, 180 degrees, 360 degrees, etc. Or as our colleague here in class mentioned, n pi radians, where n is equal to 0, 1, 2, etc. Okay? So that's the general idea there. And if you were to think about drawing these vectors on a plane with that particular orientation, here's your plane. Here's your point. And if this is your vector p, then if you were to draw another vector q, such that the cross product between p and q would be equal to 0, you could do that by having q right on top of p, or q 180 degrees the other direction for p. Both of these situations would result in a cross product between p and q, or q and p, of 0. Okay, so that's kind of an interesting result. All right, let's talk about some of the properties of these vector products. All right. Okay, very important here. Vector products are not commutative. The order matters, okay? So P crossed with Q does not equal to Q crossed with P. All right. In fact, they are just negatives of each other. But it's important just to bang home the idea that the directionality is important. Right? So if another property here, P crossed with Q is equal to V, then Q crossed with P is equal to negative V. So these are all kind of in the same vein, not being commutative. And we saw why that was. It's kind of they follow this right-hand rule, and if you sort of reverse the directionality, or you start with one way and curl your fingers the other way, or start this way and curl your fingers this way, your thumb's going to be pointing in sort of opposite directions. But generally, the magnitude remains unchanged because, you know, magnitude of Q times magnitude of P times the sine of the angle between stays the same. It's just the directionality that changes when you talk about the order of the cross product here. All right. So they are distributive. Okay. What do I mean by that? That is P crossed with Q1 plus Q2 is equal to P cross Q1 plus P cross Q2. All right. So we can distribute across, you know, a parentheses, just like you would with multiplication. Okay. However, they are not associative. And that's because of some of the directionality that occurs when you actually execute these cross products. So what do I mean by that? So vector P crossed with Q crossed with S, some other vector S, is not equal to the vector P crossed with Q crossed with S. Okay. A strange sort of thing here. Let's do a quick example where we're doing a cross product between vectors and actually sort of using numbers. And sort of maybe bang home some of these ideas and some of these principles. Okay. Actually, I'll just bring this whole thing in. Okay, here we are. So we're going to compute the vector product or the cross product P cross Q, where the vector P is of magnitude 6 units. All right, there's no units here, so we'll just call it 6 units. Lies in the ZX plane, as you can sort of see, at an angle of 30 degrees with the x-axis, and where Q is of magnitude 4, lies along the x-axis. Give you a sec there to copy down. Maybe we can put this in here, is that Q is 4 and P is 6. Okay, so we know the general magnitudes of these guys. Okay, baby. So we notice our cross product here results in a vector. So P cross Q gets us a vector V. So if we want to, fully answer this problem, we have to make sure that we know both the direction and the magnitude of our resulting vector V. So let's work through. We know the magnitude of V, and that is simply from the equation that we have, that the magnitude of V after this cross product is going to be the magnitude of P multiplied by the magnitude of Q multiplied by the sine of the angle between them, we call theta. I think it's pretty easy to see here, and I'll just be clear about this, that the angle theta in this situation is 30 degrees. All right, well, we're given the magnitude straight up here. The magnitude of P is 6, the magnitude of Q is 4. So here this is just pretty simply going to be 6 times 4 times the sine of the angle between them, which is the sine of 30 degrees. All right, punch all this in here. 24 sine 30 is going to be 12. So here the magnitude of V is 12 units. Okay, they don't really give any units here. 12 elephants. Okay. All right, but we're not done. I mean, we know the magnitude, but now we need the directionality. And the directionality, sometimes you just have to apply your cross products rules, right? Think about what's happening here. So you can see that the two vectors are contained in sort of the XZ plane here. And remember from our sort of definition of what the cross product is that the resulting vector must point perpendicular to the plane containing the two vectors. So our resultant vector will be in either the positive y direction or the negative y direction, okay? And then in order to determine whether it's positive or negative, we need to apply the right-hand rule. So remember here that we're doing our vector V is P crossed with Q. So if I'm going to follow the right-hand rule, I'm going to stand myself at the y-axis, like I'm standing on this y-axis, and I'm going to stick my arm out in the direction of P, right? So I stick my arm out in the direction of P, standing on top of the y-axis. Then I'm going to curl my fingers in the direction of Q, and we'll see here that my thumb is pointing in the positive y direction. Hopefully we can all sort of envision this. So V will be in positive y direction. Or if we're using unit vectors, positive j hat, all right? So I know my magnitude here is 12. I know my direction, positive j. So then we can say that the vector v is the magnitude of the vector, which is 12 units. And the direction that it points here is j hat. Okay, very simple example, but hopefully it's illustrative of vector products and what they are. All right. Let's keep rolling with this idea, and let's talk about relationships between unit vectors when we apply the cross product to unit vectors. Okay. So vector products of rectangular unit vectors. So when we were working in 3D and we had a force in a general arbitrary direction, usually we would figure out, all right, what is the unit vector in the direction of that force? And then resolve our force in 3 dimensions into like the X, the Y, and the Z dimensions, and then do some math in that particular space. So what we're doing here is I want to look at, okay, if I resolve my force into the X and the Y and the Z directions, and now I want to do some cross products on those particular directions, it would be helpful if I had a fast way of just figuring out, like, what if I have a component in I crossed with a component in J? Or if I have a component in J crossed with a component in K, so on and so forth. Is there a quick way for me to sort of go between all of those cross products between these sort of rectangular unit directions? So let's consider cross products, something like I cross J. And the picture you probably want to have in your head as we're doing this is a picture of a typical coordinate system. Let's go here, X, Y, Z. Notice that this is right-handed. Stick my arm in the X direction, curl my fingers towards Y. Z is going to be sort of pointing out at me. And we know that we have unit vectors associated with these particular directions, which is like I, J, K. Okay. Now my question is, what is I cross with J? Well, remember, what is the magnitude of each one of these unit vectors? Well, it's of magnitude 1. And what are the angles between these particular unit vectors? Well, it's 90 degrees. So let's consider this. So I cross J, the magnitude, will be something like 1 times 1 times the sine of the angle between I and J. Right? Well, if I'm doing I cross J, this particular angle here is 90 degrees, and it's positive. Right? So here this will be the sine of 90. So here the magnitude of this particular cross product, I cross J, is going to be 1 times the sine of 90 degrees, which is 1. So the magnitude here is just going to be 1. Obvious. Right? Now, what is the directionality of I cross J? Well, you got to think about this using the right-hand rule. So I stick my arm in the direction of I, curl my fingers in J, and my thumb will point out of the plane which contains I and J in a perpendicular axis that happens to be the Z-axis. Right? So the direction is K hat. So I cross J hat is just K hat. An important finding. We know from our rules of cross products, and you can sort of verify this yourself. If we thought about J crossed with I, what's our result going to be? Negative K. Okay. The magnitudes are all the same. The angle between them is still 90 degrees. The magnitude is 1. So the magnitude is still 1. But because of the right-hand rule now, if we go up here, we think about sticking my arm in the J direction and curling my hand in I hat direction, my thumb would point in a negative Z direction, backwards in this situation. So my directionality following the right-hand rule would be like the negative K. Okay? So yes, the magnitude is still 1, but the directionality is pointing the other direction. Okay? And this is sort of just a series of examples. I cross j is k, j cross I is k. Let's also consider the example of like I cross I. What's your idea here? 0. Okay? Because the sine of the angle between I and I is 0. So if we thought about the magnitude of this particular cross product, it would be the magnitude of I, which is 1, times the magnitude of I, which is 1, times the sine of the angle between them. And if it's the same vector on top of itself, then that angle is 0 degrees, and the sine of 0 is 0. So the magnitude of this resultant is 0. This will be important for us when we're starting to work with moments and we're doing like some component in I crossed with some component in J. All right, is that resultant going to be in the positive K or the negative K? You have to sort of like understand how we come about positive or negative directionality given the right-hand rule and these unit vectors and how it's applied. Okay, so the full picture here. If we wanted to sort of include all of the components, it would be I cross I obviously is 0. I cross j is equal to k. I cross k is equal to negative j. All right. We'll continue. J cross I is negative k. J cross j, 0. And j cross k is positive I. K cross I is positive j. K cross j is negative I. And k cross k is 0. What's that? So I have a question here in person. I don't do the chart. We're going to get to the chart. I just want to write it all out and say, wow, that's annoying. If only there was an easier way to remember. I think there's a couple of ways that people like to remember their sort of cross products of unit vectors. And I'll show you a couple different examples. I think the easiest is kind of like the Ijk circle. This is my like sort of preferred method. Remembering all this. Not really something I would want to memorize. There has to be some mnemonic or some easy way to do this. I like the Ijk circle. Okay. Which looks something like this. I, J, K. Kind of going clockwise there. Okay. And the idea is if you're kind of going clockwise around this circle, then you're going to end up with a positive. And if you're going counterclockwise, you're going to end up with a negative. All right. That's one way to think about it. Some people like to draw this in different orientations. This is the way that I learned it. It just sort of seems natural to me to go clockwise, IJK. But the idea is if you do something like I cross J, you get a positive K. If you do J crossed with K, you get a positive I. As long as you're kind of going on, this way around the circle, it's going to work out that way. So K crossed with I gets you a positive J, and so on and so forth. If you're going the other direction, like I crossed with K, you're going to get a negative J. So you're kind of going the wrong way around the circle. All right. So that's sort of one method to the madness. There's another method which is the chart method, I think, which is Yeah, I don't really know if it has a name either. It's like a matrix method or something. I don't know. But I know what you're talking about, and we're gonna get this. We're gonna get there. Okay. So this is kind of the best way to go about it. Some people draw it in other ways. I don't want to confuse you too much, but some people like drawing it this way, where counterclockwise is positive. However you remember it, just, be consistent and remember it correctly, I guess. All right. Now, that's for unit vectors, and we know that we can break down any vector into its components in I, j, and k, right? So let's extend like the idea that we just learned here to a vector that has, a variety of magnitudes in different directions. So here, vector products of components. What do I mean by this? So say we have two vectors p and q, but we're going to express them now in their rectangular coordinates. So like we have some magnitude of p in the x direction, which is an I hat, plus some magnitude of p in the y direction, which is in j hat, plus some magnitude of p z direction, which is in k hat. Similar for q. All right, we have some component of this force in the x direction, and that's in the I, some component in the y direction, which will obviously be in j, and some magnitude in z, which is in k hat. Now, if I wanted to execute the cross product of these two guys, I could do that. And we can remember for ourselves that the cross product is distributive across a variety of different components. So what do I mean by that? Then we have P crossed with Q is a little bit of gobbledygook, but Px and I plus Py and J plus Pz and K crossed with Qxi plus Qyj plus Qzk. Okay. And we can distribute this using our distributive laws of cross products, which we talked about before. We are able to distribute, but we're not able to associate. So the idea here is I could do Pxi crossed with Qxi plus Pxi crossed with Qyj plus Pxi crossed with Qzk plus Pyj crossed with Qxi plus ... You get that I could distribute here and have what would be like 9 components in my final distributive cross product with each of the individual components. And I know it's going to be a little cumbersome, but I'm going to write it all out here. So this will be something like Pxi crossed with Qxi. It's that first little bit. Plus Pxi crossed with Qyj plus Pxi crossed with Qzk. All right, that's kind of like distributing this bit to these three guys across. All right. We can do the same with the remaining components. And finally, if your arm wasn't already tired, hope you had your handwriting Wheaties this morning. Okay. Man, that's annoying. All right, let's be real. That's quite a bit there. Okay, but we can use a lot of the rules that we have for cross products to sort of simplify our life straight away. Okay, and that is, we know that if we're looking at, let's say, this particular guy here, we have some component in the I direction crossed with some component in the I direction. Okay, those two vectors are both in I. Okay, so if we take the cross product of them, the resulting magnitude is going to include like the sine of the angle between them. But if they're right on top of each other, the sine of that angle is 0. So the resulting cross product here, and we sort of talked about this already, I cross I is going to get me 0, right? So that's something you can see sort of straight away. Same thing with this like J cross J. This looks like a plus sign. Same thing with like this J cross J and this K cross K, right? All 0. We can also sort of look at the other kind of components in this fully expanded cross product here and see that, let's look at this guy, for example. You have some component of the vector P in the I hat crossed with some component of the vector Q in the J hat. And so if we know we have some component in I crossing with some component in J, that I cross J will generally give me some resultant in the positive K direction, right? By your circle of IJK, right? So the resultant will be something in positive K hat. And namely, it will be PX multiplied by QY in positive K, all right, by our sort of like magnitude rules for cross products. So we can go through this whole ordeal, and you'll ultimately end up with the following. Your resultant, P cross Q, will look something like PYQZ minus PZQY in the I hat plus PZQX minus PXQZ in the J hat plus, here we have PX QY minus PYQX in the K hat. All right. So this would be sort of like a full expansion of your cross product between two vectors P and Q, given components of these particular vectors that you might know in, let's say, the X, the Y, and the Z directions. All right. That's where we're going to stop today. I know this has been like a kind of a mathy day or math intense day. But we just got to get through this and talk about this before we actually work through some moments. So that's it for today. We'll actually dive in on real moments tomorrow. So we'll see you then. No, you're good.